Hi everyone. Today we're going to talk about heat conduction unit and how to conduct a heat conduction experiment. The unit that we have, it's provided by GONT, G-U-N-T. That's a German company. Later you're going to see that some of the units are all being based on metric, and even some of the samples that we use in this experiment are done differently than the one we have in heat conduction and heat transfer courses. The unit is meant to focus on linear one-dimensional heat conduction and radial one-dimensional heat conduction. The left-hand side setup, it's meant to have the linear case where you have a metal bar running through the white material that you see there. The white material behaves as an insulator, so this way you allow the heat only goes throughout the bar without having the second dimension or the third dimension heat transfer. So the experiment meant to have a difference in heat temperature or a difference in temperature, which is requirements to have a heat conduction or any heat transfer process. So on that side of the experiment, we have a heat element that meant to heat the one side of the metal bar that is inside this white material. And on the other side, you have a water that is running through. It's really meant to cool down the other end of the bar, the metal bar that we have inside. You can see we run the water from here. It's continuously running, as you can see right now, and at the same time we heat the element from this side. It's important to have the water running while you're heating the element, because you need to actually clear the heat out, otherwise you could get overheated inside and you start to have some failure. I know this has a safety device that can go up to at 100 degrees Celsius. It can actually shut down the system, but still we always rely on having the equipment run in the right manner. So the experiment had 3 different inserts. The one that is installed right now, this is meant to be the first insert. We call it insert 1. And this is equipped with thermocouples. So you can see right now the insert has 3 thermocouples that are numbered 4, 5, and 6. But you also have a stationary thermocouples that stay under the equipment all the time. That's 1 to 3 and 7 through 8. So those stays with us all the time. The first insert actually has the same exact dimension and material like the metal bar itself. So the metal bar is cut into 3 pieces, and we'll explain this further more in the instructions for the experiment. So the first insert actually integrate very well with the 2 sides that we have already. If you take the dimensions, you're gonna have 3 thermocouples from 1 to 3, one at 0 centimeter, exactly at the heating element. Second is located at 1 centimeter. Third will be at 2 centimeter, and you go every 1 centimeter. So the end of the first part for us right now to 3 side of the metal bar ends at 2.5 centimeters. So you have from 1 to 2 to 3, this is 2 centimeters, and then another half centimeter before we start our insert. The insert itself starts from 2.5 centimeter and runs through 5.5 centimeters. And then you have another 2.5 centimeter where you see 7, 8, and 9. Okay. You can see the equipment looked a little bit on the dirty side. This is actually due to the thermal paste that we add. You can see that like kind of a gray colored there. That's actually meant to have a very good contact, to have a higher conductivity. Otherwise, we have air gaps in between, which could create extra resistance that will affect our experiment. The second insert is going to be with the same diameter, which is the one that I'm going to hold right now, if I can. So we have here, this insert has the same exact diameter, which all like 2.5. So this part of the metal bar is 2.5 brass, 2.5 brass, and right now is also 2.5 centimeter brass. This is 2.5 centimeter of stainless steel. So your second insert, where you actually insert this piece, and you start to see how this will affect your heat conduction and the temperature gradient throughout this bar. The third insert, and this is the last insert in the linear case, has brass but with different cross-section area. If you compare here, you can see clearly that you have smaller cross-section area. This is actually 1.25 centimeter radius. So the investigation here will focus on the material thermal conductivity. Brass has a lot higher than stainless steel, so you're gonna see that the heat transfer rate can look different, and the temperature gradient also will look different when we have insert 2. Cross-section area also creates kind of extra resistance as you go smaller with the cross-section area, so you're going to see also different temperature gradient with the third insert. So the experiment is done by generating heat on the heating element, and this is by setting up the power here, and we normally go down, I don't know, 30 to 40, depends on the experiment. So for the linear, this case, we can easily handle 20 and to 30 watt. That's the power that we set up. So let me try to get it to 30. It's hard to get it exactly, but eventually you write down the value that you see. If you just end up with, let's say, between 28 and 29, you're probably going to see one number more often. To measure the temperature throughout the thermocouples, which we have 9 right now, we can just switch between one to the other. So we have now thermocouple 1 measured at 67%. I run this experiment for a little bit earlier. You can see it's going higher, and as you go, of course, higher with the temperature, you're going to see that the values gets smaller and smaller all the way to go to number 9 eventually. It's not 0, but should run differently. But one reason that we can have 1 to 6 running right now only because we have 2 different experiments that we need to hook it up on the back of the machine. The radial experiment only focus or reads 6 thermocouples, which we'll go over right now. The other way to take the data here is to go through the software that is provided by the company. You can set up the insert from this here. You have insert 1, insert 2, insert 3. Insert 1 has all the 9 thermocouples, and you should display it. Again, right now we only hooked it up to the radial case. You're not going to see anything from 7 to 9, but from 1 to 6 you can see a change of temperature that is easy to monitor here. It plots it even for you, but this is actually what you're required to do. You need to plot the distance against the temperature to show the value. We'll go over the material, that what the objectives and what you're actually looking for to determine here in this case, and usually in live streaming. Okay, so if you move on to second insert, you can see second insert has no thermocouples, and we explain why this will happen in the lecture. And we rely now on determining the temperature exactly at the beginning of the insert and at the end of the insert. We rely on the thermocouple 1 to 3 and 7 to 9 to determine the contact point on insert 2 as well as insert 3. Okay. This experiment is based on the steady state equations, and we will explain the equations in the lecture. So we have to wait enough time to make sure that the conditions became a steady state, then we can continue with our experiment. The second part of this experiment is to monitor the radial case, which is the one we see right here. Okay, you still don't see the actual experiment. It's embedded inside. The water runs through this as well. You can see thermocouples are marked from 1 to 6. This is the one that is hooked up right now. The conduction in radial direction works differently because the cross-section area, as you go bigger with the radius, gets bigger as well. So it's not like the linear heat transfer at every cross-section area. It actually gets smaller as you go farther away from the center point. The center point is located at 1. This is a 0 radius. And you go 1 centimeter at each thermocouple location, all the way to 5 centimeters at thermocouple 6. So it's done the same way. We follow the equations that are explained in the manual and in the lecture. And you can see now, if I turn this to select the circular case, you're going to see that the experiment here shows the circular case, which is what is hooked up right now. So you can see the different temperature gradient from T1 all the way to T6. So you have 45 down to 23.4, and 23.4 is very close to the water temperature that is running already, because this is where it's exposed to. So this way we'll allow to heat transfer. The equation doesn't look linear anymore, a little bit curved, and it follows a different formulation that is not linear anymore. It's actually ln function that we deal with. So this is just to give you an overview how the experiment set up, but in the lecture we will discuss further how you can obtain the right analysis. You determine the objectives, discuss the objectives of this experiment. Part of it is to verify the theory, and you compare it to the data that you get from here by determining the thermal conductivity of the material, which is given. So you're doing a comparison between what you already have compared to what the theory will give you based on the experimental setup that we have here. Okay, with this we can continue with the lecture information.